To put it simply, cloud computing allows developers and system administrators to provision computing resources such as servers, storage, databases, networking, and analytics over the internet. Cloud computing delivers on-demand computing services, often through a pay-as-you-go model. This means that computing resources can easily be scaled up and down depending on the resource requirements of the application or organization. The ability to provision resources on demand is achieved through a model known as virtualization. Virtualization is defined as the process of running a virtual instance of a computer system in a layer abstracted from the actual hardware. Advancements in this revolutionary technology serve as the primary reason behind the influx of organizations migrating from traditional on-premises data centers to the cloud. With the click of a button, system administrators are now able to deploy virtual computing instances that can easily handle the infrastructure needs of small, medium, and enterprise-level applications. A virtual instance is an emulated version of a computer system that operates through a hardware abstraction layer, or HAL. The HAL provides a computer's operating system the ability to interact with the underlying hardware devices through programs known as hypervisors. This means a virtual instance can operate as a completely self-contained computing environment on top of another system. Through abstraction, virtual instances are instantaneously able to provision any number of resources from the hardware layer. This includes any amount of CPU, memory, storage, and network resources such as bandwidth. This is why virtual cloud computing has become a viable solution for projects and organizations of just about any size, from small independent developers to multinational enterprises. There are a number of benefits to cloud computing, especially when compared to traditional physical infrastructure. As illustrated in a recent article published by IBM, the core advantages of cloud computing can be broadly defined by 5 categories. This includes greater cost efficiency, improved agility, faster time to market, greater scalability and elasticity, improved reliability and business continuity, improved performance and security. Let's start with greater cost efficiency. The ability to provision computing resources on demand substantially reduces the overhead expenses when compared with traditional physical data centers. For example, prior to cloud services, organizations would generally maintain on-premises or remote data centers. This meant that all servers and therefore computing capacity would be physically stored and maintained by the organization's system administrators. In this type of setup, administrators would often struggle with estimating the amount of computing resources they needed for each phase of the business cycle. Grossly underestimating or overestimating resource requirements would result in a significant impact to the organization's bottom line. The ongoing expenses associated with purchasing, maintaining, and housing IT infrastructure would often become problematic, especially for growing businesses that would often experience unexpected surges or drops in application usage or traffic. Cloud computing helped eliminate this issue almost entirely. This is because cloud service providers are solely responsible for the maintenance and upkeep of the data centers that house client applications and data. Furthermore, the on-demand pay-as-you-go pricing models offered by cloud vendors ensures that organizations can provision the exact resources they require when they need them. Now let's explore improved agility and faster time to market. Cloud services provide the ability to deploy highly customized virtual instances in a matter of minutes. This means they are a perfect solution for both testing and production environments and for applications of any size or complexity. Compare this with traditional infrastructure, where it would generally be a very time-consuming undertaking to physically create test systems that required a significant amount of resources for only a small fraction of time. As we will demonstrate later in this course, a virtual instance can easily be deployed instantly using various operating systems, disk configurations, network resources, and computational power. We will also showcase the ease of switching between testing and production environments using IP swapping through the Linode console. Greater scalability and elasticity. Most large-scale cloud providers operate data centers that are spread across the globe. For example, Linode now operates 11 low-latency global data centers around the world. This means applications can be deployed in close geographic proximity to end users. This translates into rapid, low-latency data access. Achieving this with traditional on-premises infrastructure would often be nearly impossible, especially for small to medium-sized businesses. This unique feature of cloud computing allows organizations to scale workloads infinitely without sacrificing performance. Improved reliability and business continuity. The global aspect of networks that power cloud data centers help ensure network redundancy. In other words, if one node in the network fails, there are multiple communication links to keep the infrastructure operational to the highest extent possible. This also allows system administrators to cost-effectively store backups of data and applications across multiple regions to protect against data loss and downtime. Most cloud providers offer both on-demand and scheduled backup services. Later in this course, we will demonstrate how to enable automated backups of storage volumes and create manual backups using disk images or snapshots. Improved performance and security. Cloud service providers generally focus entirely on maintaining and improving their cloud infrastructure. This results in data centers which are routinely updated with the highest performing computing, storage, and network technologies. Furthermore, dedicated teams are tasked with monitoring network traffic for threats, in addition to identifying and securing systems with the latest security patches. In traditional on-premises infrastructure, lax security protocols have resulted in massive data breaches over trivial issues. For example, in May 2017, credit reporting agency Equifax reported a major data breach stemming from the failure to patch a basic Apache server vulnerability. In this case, the private financial records of over 140 million Americans were compromised. In the last several years, the security offered by cloud service providers has made significant strides over on-premises security solutions. McAfee reports that 52% of companies will experience improved security when utilizing the cloud versus on-premises data centers. Although cloud vendors undoubtedly help relieve the security burden from the customer, it's important to note that the responsibility is typically shared between both parties. For example, the cloud service provider is responsible for the security of the cloud. This includes hardware and software components for its global infrastructure. On the other hand, the cloud administrator will generally be responsible for security related to operating systems, applications, firewall configurations, and customer data. This sharing of responsibility is often referred to as the shared responsibility model. You will come across this term often as you progress through the cloud space. Now that you're more familiar with some of the core benefits of cloud computing, we will explore another important concept referred to as cloud computing service models. There are three main types of cloud service models, including infrastructure as a service, or IaaS, platform as a service, or PaaS, and software as a service, or SaaS. You will likely hear these terms quite often while embarking on your journey in becoming a cloud administrator or full-stack developer. In order to better understand the concept behind cloud service models, it may be helpful to recall the components involved in a traditional on-premises setup. With traditional infrastructure, an organization would be tasked and solely responsible for all IT assets, including system hardware, software, applications, development tools, and administration. This meant the organization would purchase the necessary resources, install them, and manage them within their own data center. This is quite different from cloud computing, whereby a third party, the cloud service provider, provides customers with console access to create resources through a web-based platform. The cloud service provider then bills the customer, also known as the cloud tenant, a specified amount based on the customer's monthly resource consumption of various services on a pay-as-you-go basis. The exact cloud services and resources that an organization employs from a cloud vendor will vary depending on the organization's individual needs. However, each asset that is provisioned can be grouped into one or more of the three service models identified earlier as IaaS, PaaS, or SaaS. In this section of the course, we'll go over a quick snapshot of each service model based on the actual set of services that the model encompasses. Excellent job making it this far. Now that you have an understanding on the foundational principles of cloud computing, It's a great time to dive into some practical exercises. As mentioned earlier, we will be using the Linode cloud platform for the hands-on sections of this course. To create a Linode account, visit linode.com. Click the Sign Up button. You're now prompted to enter an email address, username, and password. I'll go ahead and fill that in. Once that's complete, go ahead and click Continue. On the next page here, we'll need to confirm our email address to continue. In your email account, click the email from Linode with the subject line that reads, "Please confirm your email." In the email, click the Confirm button. We're now prompted to input our billing information. This information is required for identity verification. Go ahead and complete the details. Once you've inputted your billing details, scroll down and input your payment information. With that complete, accept the Master Services Agreement. As noted below, a temporary hold of $1 will be used to authorize your credit card. Once you've accepted that, click Create Account. If your payment was successful, you should now be able to access your account. Go ahead and click the Go to Cloud Manager button. Great job! In this lesson, we created a Linode account. In the next lecture, we will explore the Linode dashboard. Welcome back. In this lecture, we'll be exploring the Linode admin dashboard. On the Linode dashboard, we have access to a number of important menus and options. We'll start by exploring a few important features available in our dashboard. Keep in mind that we will be working extensively with each feature as we progress through the course. To expand the left navigation menu, click the Expand Side menu icon. From the left navigation menu, we can access important services relevant to our account. We can access a list of our existing virtual instances, also referred to as Linodes. Since we haven't deployed any Linodes, we won't see anything displayed here just yet. Next, we can access our volumes. Volumes are also referred to as block storage devices. These storage volumes can be formatted and mounted to our existing Linodes. You can think of a volume as an internal storage disk. Similar to an internal disk, a volume has a fixed capacity. Adding multiple volumes is the equivalent of adding multiple internal disks to a computer. With each additional volume, you increase your overall storage capacity. In addition to block storage volumes, Linode also offers object storage. Object storage is a cheaper alternative to block storage, but it's also slower in terms of retrieval. Object storage is great for things like multimedia, archives, and data backups. We will explore the difference between object and block storage in more detail later in this course. For now, we're just familiarizing you with some important terms. In addition to creating instances and storage, we also have access to the Linode marketplace. So what is the marketplace exactly? Well, to answer that, recall that when we deploy a Linode, we're creating a virtual instance. The instance will need a few components to run. This includes an operating system and perhaps some other utilities depending on our use cases. The marketplace offers an extensive list of components that can be deployed along with an instance. This can be done at the click of a button. Some of the apps here might look familiar. For example, WordPress, LampStack, cPanel, among others. If none of this looks familiar, don't worry. We'll be using the marketplace later on to install some popular components on instances that we deploy. Next, in the navigation menu, we have the ability to access and administer our account using the account link. We're now on the account dashboard where we can see important information pertaining to our account. For example, we can see our current account balance, accrued charges since our last invoice, billing contact details, payment methods, and payment history. In addition to the basics, the account dashboard is split into multiple tabs. This includes users and grants for account user administration, service transfers. This is for transferring Linodes between multiple accounts, maintenance logs, and lastly, settings. Under settings, we have the option of closing our account down. Under the account button, we have help and support. Linode offers a number of learning aids and resources. This includes access to the community Q&A, which can often be a great place to get answers from fellow community members. We also have access to guides and tutorials, the Linode support bot, and customer support. There's a number of items here that we haven't yet addressed, and this includes node balancers, firewalls, stack scripts, images, domains, Kubernetes, and Longview. Since these items are more complex topics, we will explore them once you have a handle on the foundations of navigating Linode. We also have a top navigation menu where we can perform a number of actions. If we click Create, we can deploy a number of products. Next to the Create button, we have the option of searching our account for existing resources we've already deployed. There's a notifications bell, which displays a panel with account notifications and events. Beside that, we have a quick access menu with a number of shortcuts to commonly used services and products in our Linode account. Excellent! You're now familiar with navigating the Linode dashboard and accessing some of the common products and services that we'll be using throughout the course. In the next lesson, we'll go ahead and secure our Linode account with two-factor authentication, also known as TFA. Welcome back. In this lecture, we'll enable TFA on our Linode account. Anytime you create an account on Linode or any cloud hosting platform, it's essential to secure the account from unauthorized access. Failing to do so can result in the theft of confidential company information. Furthermore, resources deployed within the account can be permanently deleted. One of the most effective ways to secure an account is by enabling two-factor authentication. When enabled, TFA will require two different forms of authentication to log in to the Linode account. This includes a secure password along with an authorized security token generated by a TFA app, which is installed on a secondary device such as your smartphone. It's likely that you're already familiar with the concept of TFA. Many other services, such as Gmail and Facebook, encourage users to implement this form of authentication to help keep accounts secure. There are three main components to TFA. This includes knowledge. Knowledge includes things you know, such as a username, email address, password, or PIN code. The second component, possession. This includes items you possess that can be used to authenticate, such as a smartphone app or an authentication device. The third is inherence. This includes personal traits such as fingerprints or voice recognition. For the purpose of this lesson, we will work with knowledge and possession. You've already set up the account with a text password, which should only be known to you. Never share your passwords. The password is the knowledge component of our TFA. Next, we'll set up the possession component by installing Google Authenticator on our mobile device. Only you should have access to the app on your phone. The Authenticator app will display a unique authentication code each time you attempt to log in to your Linode account. Let's go ahead and get started on setting up TFA on our Linode account. To enable TFA, expand the Quick Access menu by clicking your account username. From there, click Login and Authentication. Now scroll down and click the TFA switch to enable TFA. A QR code will appear. Keep this page open since we'll need to refer back to it. Next, get your smartphone and launch the App Store if you're on an iPhone or Google Play Store for Android devices. With the App Store or Play Store opened, search for Google Authenticator and install it on your device. With Google Authenticator installed, launch the app. Now on the app, click the Get Started button and click Scan a QR code. Allow the Authenticator app to access your camera so that you can scan the QR code from the Linode dashboard. Once you've scanned the code, you'll see an automatically generated authentication token appear on your Google Authenticator app. This code will change every 30 seconds or each time you restart the app. Enter the token that you see in your Google Authenticator app in the input field over here. Once you've done that, click Confirm Token. Once you've successfully confirmed your token, you'll see an alert box appear with a scratch code. Be sure to copy this scratch code and save it securely on your computer. The scratch code will only be displayed once. It can be used in place of TFA in the event that you cannot access your TFA device. I've copied my scratch code and saved it safely on my computer. With that complete, go ahead and click Got It. The process is now complete. That's all there is to it. We can now test to make sure that TFA is working. Scroll to the top of the page and click your username and then click Log Out. Now we're back on the login screen, so enter your username and password and click Login. We're now prompted for our TFA token. So go ahead and open your Google Authenticator app from your smartphone and insert the token displayed under your Linode username. We're now logged back into our account safely and securely. Great job! In this lesson, you learned how to enable TFA on your Linode account. In the next lesson, we will dive into deploying a virtual instance. Welcome back. In this lesson, we will deploy and configure our first Linode virtual instance. To get started, make sure you're on the Linode's dashboard by clicking on the nodes. From the dashboard, click Create Linode. We're now prompted to configure some important options for our Linode. The first thing we need to specify is the distribution image for our instance. This refers to the operating system we want deployed on the root volume of this instance. Images refer to pre-configured disks that can be used to rapidly deploy an instance. The image comes pre-configured with an operating system and standard software settings that are required for most applications and workloads to execute. In case you're wondering, we can create our own images, which we'll do later on. However, for now, it's much easier to select a pre-configured disk image that is available in your account. Another important note is that the root volume is the default volume that is attached to an instance on deployment. A root volume is not optional. However, additional volumes attached to the instance are optional. With that said, let's go ahead and select the latest Ubuntu distribution for our instance. From the drop-down menu, select Ubuntu 20.04 LTS. Ubuntu is a popular Linux distribution, especially for hosting web applications. We will explore Linux in greater detail in a future module. Next, we need to specify the data center where the instance will be deployed. Recall that you generally want to deploy a server which is in close proximity to your end users. This helps maximize speed and reduce latency. For the purpose of this lesson, I'll select Newark, New Jersey. Next, we need to specify the Linode plan. When deploying a Linode instance, you'll need to consider how much of the following resources your application may require. The resources include RAM, CPU, SSD storage, and monthly transfer or bandwidth. Linode charges based on resource usage at a prescribed hourly rate, up to a maximum threshold. For example, the most basic Nanode 1 GB plan would be billed at a rate of 0.0075 cents per hour, up to a monthly maximum of $5, assuming there are no overages. Selecting the right plan for your needs is important because you don't want to deploy a server that exceeds the amount of resources you intend to use and incur unnecessary charges to your account. Keep in mind that due to the scalability of virtual instances, we can always upgrade or downgrade our plan in the event that more or less resources are required in the future. Let's take a look at the Linode instance configurations we can deploy, which are listed under the Linode Plan panel. Here, we can select the exact specifications for our initial instance deployment. The configurations are broken into 4 sections, including the following. Dedicated CPU. The dedicated CPUs are best used when you need peak speed and efficiency, or when no other instances can run processes on the same cores. Another example is if you need CPU-intensive game servers like Minecraft or Team Fortress. Use dedicated CPUs when you need audio or video transcoding and streaming. Other examples include big data and data analysis, scientific computing, and machine learning. Now, beside dedicated CPU, we also have shared CPU. Shared CPUs have very broad use cases, from personal projects to enterprise apps. We can use shared CPUs for websites and web applications, code repositories, game servers, database servers, virtual private networks, and container clusters. Next, we have high memory. You'll want to use high memory for workloads that require higher RAM allocations and relatively fewer CPUs and less storage. So these are typically used for in-memory caches and in-memory databases like Memcached and Redis. These are also typically used for storing web applications and analytics data. For example, user session logins and frequently requested pages. Next over, we have the GPU plans. These are extremely high performance. Only GPU plans provide access to NVIDIA Quadro RTX 5000 GPU cards. These are designed to process large blocks of data in parallel. They're best for workloads requiring thousands of simultaneous threads. GPU-optimized instances can perform computations and process large amounts of data in parallel. They're great for specialized applications such as machine learning, artificial intelligence, video transcoding, and big data. I'm going to hop back over to the shared CPU plans. For the purpose of this lesson, and mostly throughout this course, we'll be using the basic configurations. So I'm going to select the 1 GB Linode plan. This plan comes with 1 GB of RAM, 1 CPU, and 25 GB of storage on our root volume. With our plan selected, we can now assign a label to this Linode. Let's call it test VM. We don't need to apply any tags. Now we'll need to assign a root password to remotely access and administer our instance once it's deployed. It's important to input a strong password and keep a note of it because we'll be using it later on. Once you input a strong password, you'll see it reflected in the password gauge down below over here. Once you see the password gauge set to good, you'll know that the password is acceptable. As an added layer of security, it's always a good idea to create machine-generated SSH keys that can be used as a more secure method of remote authentication. However, since we have a section dedicated to server security, we'll skip this for now. We don't need to attach a VLAN or add any of the add-ons such as backups and private IPs. We'll be doing this later in the course. With our configuration complete, we can see a brief summary of the settings that we've configured for this instance. We're launching the instance in Newark, New Jersey. We're using a pre-configured Ubuntu 20.04 LTS disk image. And the instance will be deployed with 1 CPU, 25 GB of storage, and 1 GB of RAM. And the label that we've attached to this instance is test VM. Now go ahead and click Create Linode. Our new Linode is currently provisioning, so we'll have to give it a minute. And once that's complete, we'll go ahead and explore this Linode instance dashboard. So we'll see you in the next lecture. Welcome back. In this lesson, we'll explore the Linode instance dashboard. After creating our instance, we were automatically taken back to the instance dashboard. The provisioning status for our test VM instance has now changed to running. This status will only change to running if the boot sequence of the instance is successful after deployment. The information displayed here is specific to the test VM instance. In case you lose this page, you can always access it again by following these steps. Click Linodes on the left navigation menu. Here we can see a listing of all our Linodes in our account. We only have one right now. Click on the test VM instance. We're now taken back to the test VM analytics dashboard. The dashboard contains some important information relevant to our instance deployment. This includes a summary of the resources allocated for this instance, the public IPv4 and IPv6 address for the instance, the SSH access command when using third-party SSH clients for remote administration, and the SSH command to access the Linode instance via LISH through SSH. We'll elaborate more on this later in the course. Next, we can see our existing Linode plan, the region of deployment, the Linode ID for the instance, and also the date it was deployed. The instance summary panel also includes the option to power off the instance, reboot the instance, and launch the Lish console. Below the summary panel, we have a number of other tabs. This includes Analytics, Network, Storage, Configurations, Backups, Activity Feed, and Settings. The Analytics section offers a summary of resource usage based on a specific time frame. We can set the time frame from the pull-down menu at the top right corner of the panel. Currently, the options available are 24 hours or 30 days. There are 4 monitoring graphs in the Analytics section. The CPU summary offers a graphical representation of CPU usage as a percentage of the total CPU available under our Nanode plan. Along the x-axis, we can see the time range. The y-axis represents the CPU usage in percent. The disk I/O blocks per second represents the read and write processes on the root volume within the specified time period. The disk I/O is measured in blocks per second. This unit of measurement is reflected on the y-axis of the graph. The network IPv4 and IPv6 graphs indicate the total network usage in bytes per second, which is reflected on the y-axis of both graphs. Looking at the summary below the graphs, we can see a number of categories. Public in refers to the volume of traffic coming into the network interface from outside internet sources. Public out refers to traffic originating from our network interface, or in other words, uploaded to outside internet sources. Private in and private out refers to internal network traffic between multiple Linode instances. For example, any data transferred from one instance to another within Linode's data centers and internal network infrastructure. Since we only have one Linode, there would be no private network usage. In addition to the Analytics tab, we can also retrieve important network information under the Network tab. If you see a number of alerts at the top taking up space on the screen, just go ahead and close them with the X. So under the Networks tab, we can monitor our monthly network transfer to make sure our existing plan is sufficient for our use case. Using more monthly transfer than the plan allows results in overage charges. For this reason, it's a good idea to keep tabs on this information. Underneath the monthly transfer panel, we have the IP addresses panel. Here we can see a list of IPs associated with our current instance. This includes our public IPv4 address and IPv6 address, along with our local IPv6 address. We're also given some important administrative tools where we can transfer IPs between Linodes, share a single IP between multiple Linode instances, and add or delete an IP address. These are all very important features, and we'll be exploring them in detail later in this course. The Storage tab is the third important section in our Linode instance dashboard. Here, we can see each root disk attached to our instance in addition to any other volumes we've created. We currently have one root disk with a total capacity of 25 gigabytes as reflected in the size column next to our Ubuntu disk. Out of this 25 gigabytes, 512 megabytes is automatically allocated towards our swap disk. A swap disk is a temporary storage space that is used if the system runs low on memory. If a swap disk is used too frequently, it can indicate that it's likely time to upgrade your current configuration. We can rename each of these disks by clicking the Rename button. For the purpose of this example, I'll update my Ubuntu disk name to main disk. Once I click Rename, you'll notice that the name updates immediately. In addition to the root disk, we may need to add additional block storage volumes. We can do so by clicking Create Volume under the Volumes panel. After you click Create Volume, an Options panel appears. We now have the ability to create and attach a new volume to our test VM or attach an existing volume to our test VM. Since we don't have a volume outside our root disk, we'll select the first option, Create and Attach Volume. That's the default, so you don't need to do anything right now. Insert a label for the new volume. Let's go ahead and call it Test Volume. Now we need to specify a size for the volume. I'll go with the minimum, which is 10 gigabytes. Config simply means that this volume will be associated with the Ubuntu 20.04 disk profile, which was created when we deployed our instance. We can see that this volume will cost $1 per month on top of our existing plan. Go ahead and click Create Volume. You will notice that the status in the panel updates to volume scheduled for creation. We also have some important information that will be more relevant when we use our volumes in future exercises. For now, you can go ahead and close the panel. The test volume now appears under the Volumes heading and has been successfully attached to the test VM. In the Volumes row, we can see the volume label, region, size, and file system path. We can also view the configuration rules for the disk and edit the disk label. Clicking the three dots here reveals an additional panel with options to resize, clone, detach, and delete the volume. Excellent. We can now move on to the remaining panels. Go ahead and click the Configurations tab. This tab provides a list of our current disk configuration profiles along with the disk path in our file system. A configuration profile is a set of configuration settings which was pre-built into the disk image we selected when deploying this instance. The settings and parameters embedded in the profile would have been configured by the author of the disk image. To edit the configuration of the default profile, we can click the Edit button. This launches a panel with a number of settings. Since most of these settings are beyond the scope of this course, we can exit the panel and leave the parameters as default. In addition to editing the default profile, we can also add a configuration profile by clicking the Add Configuration button. When you click the Add Configuration button, you'll see another panel appear asking you to configure a number of parameters, but go ahead and close that for now as well. To clone or delete a configuration profile, launch the Quick Access menu by clicking these three dots here. We now have the option to clone and delete this configuration profile. Next to the Configurations panel, we have Backups. Here, we have the option of enabling the Managed Backup service administered by Linode. By enabling the service, Linode will periodically create backups of the disks attached to this instance. Since we'll be working extensively with backups later in the course, we can skip this for now. Next to the Backups panel, we have the Activity feed. This section offers an event log of every action taken in your Linode account. We can see the event that took place, along with the duration of the event and when it happened. If you ever suspect any suspicious activity within your account, the activity feed can be a useful source of information. The last section in our Linode instance dashboard is the Settings panel. Here, we have the ability to perform some important administrative tasks on our instance. First, we can update the instance label. Next, we can reset the root password for our boot disk if needed. Below the password reset panel, we have the notification thresholds section. Here, we can specify when notifications should be issued based on certain usage thresholds. Notifications are sent via email. By default, we will receive the following notifications: when CPU usage exceeds 90%, when our disk read and write rates exceed 10,000 IOPS, when our incoming and outgoing traffic exceeds 10 megabytes per second, when our network transfer quota exceeds 80% of the allowable usage under our existing plan. To turn off specific notifications, we can do so by toggling the blue switches. When it becomes grayed out, that means it's off. Anytime you make changes, make sure to hit the Save button for the changes to take effect. After the Notification Thresholds panel, we have the Shutdown Watchdog. If enabled, Linode will automatically reboot the instance if it powers off unexpectedly. Lastly, we have the option to delete the instance altogether. This will result in permanent data loss. The disk profiles and boot disks associated with the instance will be permanently deleted. They can only be restored from backups or custom images, which we will explore later on. Well done! You've now gained quite a bit of experience in navigating important aspects of the Linode instance's dashboard. With this section complete, let's navigate back to the main Linode's dashboard. In the next lesson, we'll explore how to connect to a Linode instance. In this section of the course, you'll learn different ways to securely connect to a Linode instance in order to administer it. Instance administration refers to a number of different things. Here's a list of just a few reasons why you may need to connect to your instance. You may need to update the operating system. You may need to install, update, or remove software packages and service applications. You may need to create, delete, or modify system files and directories. You may need to monitor system performance and other analytics. You may need to install and configure security patches and firewalls. This certainly isn't an exhaustive list, but it gives you a general idea of use cases. Unlike your local computer, which is in your home or office, an instance is located in a remote data center. This means, in order to execute commands, we require a connection to the instance. To start off, we'll be connecting and performing actions through the command line executed through web-based and software-based connection utilities. This might be different than what you're used to. With your local computer, you hook up a monitor and have a graphical interface that can be navigated with a mouse. In future exercises, we'll show you how to install a graphical UI on your instance. However, for the time being, we'll only cover the basics using the command line. Hopefully you now have a foundational understanding of the purpose behind connecting to an instance. In the next lecture, we'll explore password versus SSH key authentication. Before we go ahead and connect to our instance, it's important to understand how to do so securely. When we initially deployed our instance, you might recall that we configured a root password for authentication into our server. Unfortunately, even if you entered a very strong password, plain text passwords are often not secure enough on their own. Passwords are susceptible to brute force attacks. This is where an attacker attempts to log into your instance by systematically submitting different combinations of characters until the correct combination is found. Although there are several ways in which brute force attacks and other password-related security vulnerabilities can be addressed, one of the most effective is by implementing SSH key authentication. This method of authentication can be performed through remote login utilities included as part of the open source Open Secure Shell or OpenSSH suite of software tools. More information regarding the OpenSSH project can be found at openssh.com. However, to simplify its core function, the OpenSSH project is described by IBM as an open source version of the SSH protocol suite of network connectivity tools. As stated in the OpenSSH project documentation, the suite contains a number of tools for remote server operations, including the following: the OpenSSH Remote Login Client, the OpenSSH Daemon, OpenSSH Secure File Copy, and OpenSSH Secure File Transfer. OpenSSH also includes a host of encrypted key management utilities, including SSH-ADD, SSH KeySign, SSH KeyScan, and SSH KeyGen. Although we won't be exploring each one, we will work with SSH KeyGen to generate keys later in this course. Another point worth mentioning is that the SSH client for secure remote connections is installed on most, if not all, Linux distributions and Mac OS by default. If you're on Mac or Linux, you can easily determine if your system has the client installed by opening up Terminal and typing in which SSH. If you see the following output, this indicates that the client is installed. Now, if you're on a Windows machine, not to worry. We'll be installing a utility called PuTTY later on, which supports SSH connections through a terminal emulator. We'll also be installing PuTTY-Gen for generating key pairs on Windows. It's worth noting that the SSH Secure Shell protocol facilitates client-server connections over TCP. The SSH protocol is the most trusted remote access open source network protocol used by system administrators to remotely administer servers. As stated in the manual pages for the latest OpenSSH release, the SSH2 protocol implemented in OpenSSH is standardized by the IETF, which is an acronym for the Internet Engineering Task Force. The protocol's architecture works on 3 layers, which include the following: the transport layer, the authentication layer, and the connection layer. This illustration exemplifies how these 3 layers work in order to facilitate a secure encrypted connection. As shown in this illustration, the first thing we have is an SSH client. This client is an application stored on our local machine. The client is used to initiate and negotiate a connection between the client and remote server. During this process, a key exchange takes place, which results in an encrypted connection for the purpose of preserving integrity and confidentiality between client and server. The authentication layer utilizes the established connection and operates on top of the transport layer. It's used to facilitate mechanisms for user authentication. Two common forms of authentication include traditional password and SSH key authentication. Since we're primarily concerned with SSH key authentication, let's take a closer look at how it works. With SSH key authentication, we have two important elements, a private key and a public key. A private key is an encoded stream of random bits that is contained within a key file and is stored on the client's computer. This file should be kept secret and never shared. The public key is another stream of bits that is derived from the private key. In other words, we can generate a unique public key from a private key, but not vice versa. It's a one-way process. The public key is stored on both the client and the server. The unique connection between the private and public key is the reason they are referred to as a key pair. A successful login operation occurs when the private key is used to successfully decrypt the public key. Now let's move on to the connection layer. The connection runs on top of the authentication layer and manages, among other things, the SSH session. Now that you understand a bit more about the SSH protocol and OpenSSH tools, here's a list of important use cases for SSH that you will likely encounter at some point. The first use case is to secure remote access to resources on an instance. We can also use it to secure file transfers between computers over a network. It can be used for remote execution of commands and the delivery of software patches and updates. Well, there you have it. You're now familiar with the basic theory behind SSH key authentication. Hopefully this lesson has given you some valuable insights into using SSH keys over basic password authentication. In the next lecture, we'll go ahead and create our SSH keys and establish a secure connection to our Linode instance from our local computer. Welcome back. In this lesson, we will demonstrate how to generate an SSH key pair on a Windows computer and connect to our Linode instance remotely using PuTTY Terminal Emulator and PuTTY Key Generator. To get started, create a folder on your desktop called PuTTY. Next, visit the putty.org website and click Download PuTTY. Now scroll down the page and we're going to download the 32-bit version. So where it says putty.exe, right click on the link and click Save Link As. Now you're going to save this file in the PuTTY folder we created earlier. When you've opened the correct folder, just click Save. Now we'll need to scroll further down the page until we come across PuTTY. We're going to download the 32-bit puttygen.exe file. So right click on the link, Save Link As, and we're going to save it in the same folder as the putty.exe file. Just click Save. We're now going to launch puttygen.exe. So navigate back over to your desktop, open the PuTTY folder, and double-click puttygen.exe to open it. We're going to use puttygen.exe to create the SSH key pair. To get started, we're going to leave most of the settings as default with one exception. Change the number of bits in a generated key from 2048 to 4096. Now click the Generate button. Make random mouse movements to generate a unique key. Just keep moving your mouse until the process is fully complete. Our public key has now been generated, and you can see it in this input area here. Now position your cursor anywhere within this output area, right-click, and go to Select All. That'll select the entire key. Copy this key and paste it into Notepad. We're going to save this file in our PuTTY folder. Once you've navigated over to the PuTTY folder, create a new folder and call it SSH key. Inside the SSH key folder, save this file as Linode_public, and the txt extension will automatically be added. So just go ahead and click Save. With the public key created, we can now generate our private key. You can leave this notepad file minimized for now. We'll refer to it later. So we'll now go ahead and generate our private key. First, enter a key phrase. The key phrase can be any combination of alphanumeric characters. Make sure it's something that you'll remember. Once you've entered the key phrase, confirm the passphrase. With that complete, click Save Private Key. Now you're going to navigate back to the PuTTY folder that we created on the desktop. Inside the PuTTY folder, open up the SSH key directory and save this file as Linode_private. The extension that will automatically be applied to this file is the .ppk extension. So go ahead and press save. Our key pair has now been generated, so we can go ahead and configure PuTTY to establish a secure connection to our instance. To launch PuTTY, open up the PuTTY folder and double-click putty.exe. Now we'll go ahead and configure the settings to connect remotely to our Linode instance. From the category menu on the left, expand the SSH option and click on Auth. Now what we're going to need to do is locate the PPK file that contains our private key. So click Browse, and we're going to navigate back over to the PuTTY directory. Inside the PuTTY directory, open up SSH key, and you're going to select Linode_private.ppk and click Open. This is the private key file we'll be using for this connection, and now it's going to be stored here for us for future reference, so we don't need to worry about it beyond this point. Now scroll up in the category menu and click Session again. Now we'll need to enter the IP address of our Linode instance. The IP address for our instance can be found in the Linode's manager. So if you haven't done so, you'll need to navigate back to your Linode manager and just copy this IP address here. Now paste that IP address inside the host name or IP address input area. Make sure the connection type is set to SSH and that the port is set to 22. We're going to save this session so that we can pull up these configuration details anytime we want to connect to our instance. And we're going to name the session Linode. So just type in Linode in this input area and click Save. And then you'll see Linode appear in our connections list. Now go ahead and click Open to establish the connection. So the first thing you'll see is a PuTTY security alert and this is nothing to be concerned about. Just go ahead and click accept. Now we're in the PuTTY terminal emulator. Since we're trying to establish a connection, the first thing we'll need to do is enter our username and password. So we're going to log in as the root user. So type in root and press enter. You'll notice a message that says server refused our key. This is expected because we haven't finished setting up SSH key pair authentication. For now, we'll need to log in using the password that we configured when this instance was deployed. So once you've entered your password, press enter. And then you should be logged into your instance. I'll go and expand the size of this window a little bit. Now that we're logged into our server, we can start executing commands to the server. The first thing we want to do is configure the server to authenticate with our SSH key pair instead of the root password that we'd used to log in. And the root password was configured when we deployed the instance. Now, in order for SSH key pair authentication to work, we'll need to upload our public key, the public key that we generated earlier. We'll need to upload it to our server. To do so, we'll first start off by creating a .ssh directory in the home folder of our Linode instance. We'll then create a blank authorized keys file and paste our public key in this newly created file. We'll also need to set the read and write permissions of the authorized keys file so that it can be accessed. So let's go ahead and do that. To make the directory that will store the authorized keys file, type in the following command. Once you've entered the command, go ahead and press enter. So in our last command there, we made a directory, the .ssh directory, and we created an authorized keys file within this directory. The next thing we'll need to do is modify the permissions of the authorized keys file. To modify the permissions, type in this command. This is the chmod command, and we'll be working with this later on. So here we're setting the permission of the .ssh directory and also the permission level of the authorized keys file. So once you've inputted that command, go ahead and press enter. We've changed the permission from 600 to 700 for the authorized keys file. So again, don't worry if you don't know what that means for now. We'll be working with permissions later in this course. For now, you just need to know that we've modified the permissions so that the file has the correct read and write permissions, so that this SSH key pair authentication can work. Let's go ahead and confirm that our authorized keys file was indeed created. And to do that, you're going to type in cd/root and press enter. This command opens up the system's home directory where we created the .ssh folder. Now type in cd.ssh and press enter. Now type in ls and press enter. So the ls command is the list command. It's going to list the contents of the .ssh folder that we created. And inside the .ssh directory, we can see the authorized keys file. We'll need to edit the authorized keys file so that we can paste our public key in this file. To make changes to the authorized key file, we'll be using the Nano text editor. And to use Nano, simply type in Nano and then the name of the file and press enter. We've now opened up the authorized keys file in Nano, and all that's left to do is paste our public key inside of this file. So go ahead and open the Linode _ public.txt file. This is the one that we'd saved earlier. Copy the contents of this file. Make sure to copy the entire key. To paste the key in the authorized keys file, position your cursor inside the terminal emulator and just press the right mouse button, and that will paste the entire key inside the authorized keys file. Once the key is pasted inside this file, we can exit the file. To do so, press Ctrl X. You'll be prompted with a message that asks if you want to save the modified buffer. Make sure to input Y and then press Enter. So we're just going to now open that file again to double check that our public key did save in the authorized keys file. So press the up arrow key on your keyboard, and that's going to call the last command that we'd used. Press Enter again, and we can see that the key is in fact stored in the authorized keys file. So we're ready for the next step. So we're going to exit this file again, just press Ctrl X. And this time we didn't make any changes to the file, so it didn't ask if we wanted to save the changes. Now that our public key is stored in the authorized keys folder, our SSH key authentication should work. We have our private key on our computer and the public key stored in our remote Linode instance. So we're going to exit this session. Just type in exit and press Enter. Now we're going to open up PuTTY again. We already have all our connection settings saved for our Linode instance. All we need to do is select Linode and click Load. And you'll notice that it automatically populates all the connection parameters that we configured earlier. So once that's loaded, click Open. And we're still going to log in as user root because we don't have any other users at the moment. Press Enter. Now we're authenticating with our key pair. So this time we need to enter the passphrase for our key. And this is the passphrase that we'd configured inside PuTTY, not to be confused with your password that you'd configured when you deployed your instance. So enter the passphrase and press Enter. Okay, I'll try that once again. I must have made a typo. And perfect. So now I'm logged into the server using SSH key authentication rather than password authentication. Welcome back. In this lesson, we will demonstrate how to generate an SSH key pair on a Mac or Linux system and connect remotely to your instance using Terminal. Let's get started. First, we need to launch Terminal. To do so, press Command plus the spacebar to launch Spotlight Search. Type in Terminal, select the Terminal app, and press Enter to open it. Next, we need to generate our SSH key pair. This includes both our public key and private key. To do so, type in the following command: ssh-keygen-b 4096. The value 4096 specifies the number of bits to use when generating the key pair. 4096 bits is recommended for a high degree of security. Now press Enter. You'll see a status alert indicating that the key pair is being generated. We're now prompted to enter a file in which to save the key. To use the default names, press Enter. The default names are ID_RSA for the private key and ID_RSA.pub for the public key. You'll only want to enter custom names if you've already used the default names for another key pair which you actively use. I'll go ahead and press Enter to use the default names. Next, we're prompted to enter a passphrase for the key pair. This adds an additional layer of security and ensures the key pair cannot be used without the secure passphrase. Enter a passphrase and press Enter. The passphrase can be any alphanumeric combination of characters. Now we'll need to confirm the passphrase. Press enter again. Perfect. Our key pair was successfully generated. To confirm that the key pair is in fact in the .ssh folder we created, type in the following command and press enter. Now type in ls and press enter. This will list the contents of the directory. Here we can see that the ID_RSA private key and the ID_RSA.pub public key are in fact present in this directory. With our keys generated, we need to copy the public key to the root user's .ssh directory on our Linode instance so that it can be used to authenticate with our private key, which is stored on our local computer. In order to do this, we'll be using the ssh-copy-id command. This command offers a secure and efficient way to install an SSH key as an authorized key through the execution of a single command. Type the following command into terminal and press enter. Now here I'm about to type the IP address for my Linode instance. The IP address for your instance will be different. To find the IP address for your Linode instance, you'll have to visit your Linode manager. So I'll show you how to do that. Here I am in the Linode manager, and under the IP address column, simply press the copy button. This is the IP address for your Linode instance. Now back in terminal, I'll go ahead and paste that in. And with that complete, I'll go ahead and press enter. The installation process will now start automatically. You'll be prompted to confirm that you want to continue connecting to the server. Just type in yes and press enter. To complete the installation, we'll need to enter the password for the root user. Now this is not to be confused with the passphrase, which we configured a moment ago. This is the password that you configured when you initially deployed your instance. So go ahead and type that in. And press enter. If the installation was successful, you will see a status message which displays the number of keys added. The value corresponding to this message should be 1. At this point, we're automatically logged out of the session so that we can reconnect using our SSH key. To reconnect, type in the following command. And again, you'll need to now type in the IP address of your instance. Make sure you don't use the IP address I'm using. So this time, we're now prompted for the passphrase. And this is the passphrase that we configured when we started this process. This does tell us that SSH key pair authentication is working as it should. So go ahead and enter the passphrase and press enter. You should now be connected to your instance through a secure SSH connection. Great job! In this lesson, you learned how to create SSH key pairs using terminal. You also learned how to connect to your instance using terminal and SSH key authentication. We'll see you in the next lecture. Welcome back. In this lesson, we will demonstrate a third method to remotely connect to your instance in order to administer it. This time, we'll be using Linode's web-based Lish console. This convenient console can be launched directly from the Linode Cloud Manager. Let's get started. To launch Lish, visit the Linode Cloud Manager and visit the Linode's dashboard. Expand the Instance Quick menu and select Launch Lish Console. You'll see the Lish console window appear. We're now prompted to enter our login credentials. For the username, enter root and enter the password you selected for this instance when the instance was deployed. Once you've typed in your password, press enter. And so as you can see, we're logged in, and we can now execute commands to our instance the same way we would using terminal or PuTTY. Although the Lish utility is a handy tool for quick and easy console access, it's generally recommended that you connect to your instance using PuTTY or terminal from your local computer. For example, if you were to accidentally leave the console open in an unsecure location, somebody could gain access to your server and wreak havoc by executing malicious commands. So anytime you do launch the Lish console, you'll definitely want to terminate this session by typing in exit and pressing enter. You're now logged out of the session and you'll need to log back in. And once you're logged out, you can go ahead and close the Lish console window. Well done. In this lesson, you learned how to remotely connect to your instance using the Lish console. We'll see you in the next lecture. Welcome back. In this lesson, we'll demonstrate how to add SSH public keys to the Linode Cloud Manager. So far, you've learned how to generate SSH key pairs using PuTTY-Gen for Windows and Terminal for Mac and Linux. In the previous exercises, we created a public key and manually added this key to an SSH folder on our instance. If you intend on deploying a number of instances, Linode offers a much more efficient way to add your public key to each instance directly on deployment through the Linode Cloud Manager. In this lesson, we will demonstrate how to add public keys to your account in order to provision them for future instance deployments. Let's go ahead and get started. First, you'll need to access your Linode Cloud Manager. From the Quick Access menu at the top right-hand corner, select SSH keys. Now click Add an SSH key. We'll need to enter a label for the key. I'll go ahead and call it main key. With the label created, we can go ahead and paste our SSH public key in this input area. I'm going to pull up the public key that we'd saved earlier in our PuTTY directory on the desktop. So the file name is linode_public.txt. I'm going to copy out this entire key, and I'm going to go ahead and paste it in this text input. Just keep in mind that if you are on a Mac system, then you'll need to copy the public key that we generated on your Mac computer. So with that complete, I'm going to go ahead and click Add Key. The public key is now immediately added to your account for future use. To use this key for future instance deployments, we can do the following. Click on the Create button. Now click Linode. So if we were to create a new instance right now and we wanted to use the SSH key that we saved to our account, we would scroll down, and under the SSH keys heading, you can see that the public SSH key we added to our account is now available to be used for this deployment and all future instance deployments. All we would need to do is place a check mark, and that public key would then be added to that instance deployment. Since we don't need to launch a new server right now, let's head back to the Linode's dashboard. Great job. In this lesson, you learned how to add an SSH public key to your Linode Cloud Manager, which can be used for future instance deployments. In the next section of this course, we'll be exploring Linux in more detail. Understanding the role web servers play in the lifecycle of the development process is an important building block towards becoming a full-stack developer. In this lecture, we will explore the role of web servers and the integral role they play in hosting and delivering web content to application end users all over the internet. To begin, it's important to separate the two components which enable the operability of a web server. This includes hardware and software. In respect to hardware, a web server is a physical or virtual computer which stores the web server software along with the files and components that comprise the website or application. This includes things like static HTML documents, text files, images, video content, and dynamic scripts. The web server is connected to the internet and facilitates the digital interchange of data with other devices connected to the web. The web server software, which is installed on the physical or virtual machine, controls the accessibility of files on the server by web users. Web users use clients in order to connect with web servers and view web content. The most common client used for this purpose is a web browser. The communication protocol used in order for a web browser to communicate with a web server is the Hypertext Transfer Protocol, or HTTP for short. HTTP is responsible for encoding and transporting information between a web server and the client used to access it in the form of data packets. HTTP is the primary protocol for transmission of information across the internet. HTTP utilizes a request-response mechanism whereby a client makes a request for content and the web server issues a response. The response includes information pertaining to the status of the request along with the content requested if successful. The information contained within a request is exchanged between the client and server in the form of hypertext documents. Hypertext is a structured text format that can be manipulated using the Hypertext Markup Language, or HTML. Using HTTP requests along with HTML documents, clients can request different types of content from web servers. This includes text, images, video, and application data. Let's take a look at an illustration which demonstrates how an HTTP request made through a web browser can retrieve an HTML web page. On the right side of this illustration, we have a web browser, the client, which makes an HTTP request to an HTTP server. The request is made by typing in a uniform resource locator, or URL, into the web browser address bar, for example, google.com. The human-readable domain is then mapped via DNS to the IP address of the web server, which contains the google.com website. If the physical server is found at the IP, the web server software accepts the HTTP request and responds with the requested document. In this case, the Google homepage. This is what the end user sees through their web browser after the sequence of events is complete. As outlined by the Mozilla Developer Guide, there are a few clearly defined rules as to how a client and server communicate. This includes the following. Generally, only clients make HTTP requests to servers, while a server responds to a client's HTTP request. A URL must be specified when a client makes an HTTP request to a server. When an HTTP server receives a request, it checks whether a file at the specified URL exists. If the file matching the URL exists, the web server will send back the file contents to the client's web browser. Otherwise, the web server returns an error message commonly referred to as a 404 not found. Every HTTP request must be answered by the server even if the request fails. Excellent. You've now gained a bit of foundational knowledge. You've now gained a bit of knowledge on web servers. In the next lecture, we'll talk about self-hosting versus using a hosting provider. At this point, you might be wondering why you need a hosting service provider to host websites or web applications if it's just a computer configured as a server. Meaning, why not just use your home computer and save a few bucks? Well, with the right technical expertise, you absolutely can use your home computer as a web server to serve web content. However, there's a few reasons why this might not be the best idea. Let's go over a few reasons why this might not be the best solution for your needs. The first is internet speed. Depending on your internet plan, you may not have the speed and bandwidth necessary to share data from your server with a large number of users over the internet. This is especially true if your internet package does not include robust upload speeds. Remember, anytime a website visitor requests a file from your web server, your server is uploading the file to their computer. Most retail internet plans are focused more on offering high download speeds, but only marginal upload speeds. The next pitfall is power consumption or power failure. Depending on the type of computer system you own and the resource consumption of your web app, operating it continuously each day will generally increase your electricity consumption. It's quite likely that your home or office computer doesn't come equipped with a backup power generator. Now let's talk about backups. Generally, when running a dynamic web application, the application data is constantly changing. For this reason, you may need to configure a storage device for backing up data in case the primary disk fails. This adds further complexity, increases costs, and can take up more physical space in your home or office. Dynamic versus static IP. Most ISPs assign a dynamic IP for your home network. This means the IP address automatically changes at various intervals. When running a web server, it's preferable to have a static IP that always stays the same. Most ISPs do offer static IPs, but they come at an additional cost. Configuring a server to automatically update DNS records every time a dynamic IP changes is possible, but requires some technical expertise. Another important consideration is security. A personal office computer generally has private information that you wouldn't want shared with the public. When converting your computer into a web server, you're allowing internet users to connect to your system over a public network. Without the right security measures in place, this can open up a number of system vulnerabilities that can be exploited by an attacker. Scalability. As your web application and resource needs expand, you'll need to scale up your hardware. This means purchasing additional equipment, increased power consumption, and a number of other complexities which accumulate as application load increases. Lastly, we have liability. In some cases, you may be hosting files and data that belongs to a third party. In this case, you may be solely responsible for security. Lax security measures can lead to data theft, which can make you liable. Awesome! You're now familiar with how web servers work and also some of the pitfalls of running a home-based web server. In the next lecture, we'll explore some of the most popular options available when it comes to web server software. When it comes to configuring a web server, there are two HTTP web server software solutions that currently dominate the market in terms of usage. This includes NGINX and Apache. Combined, they currently account for over 65% of the market share. These statistics are available through W3Techs at the URL shown here. If we navigate over to the page, we can see the usage dominance per category for all websites across the internet. NGINX holds the top spot at 33.8%, followed by Apache at 31.4%. Since this trend only continues to grow, the focal point of this course will be on these two web server technologies. Let's go through a side-by-side comparison of NGINX and Apache in order to learn a bit more about each one. Since both technologies are better suited for different purposes, the information we cover here will help you determine which solution is best for your individual use case. Apache was founded in 1995 by Robert McCool, whereas NGINX was founded in 2002 by Igor Sysoyev. Both projects are completely open source. Apache is managed by the Apache Software Foundation, and NGINX is developed and maintained by NGINX Inc. Apache was designed primarily as an HTTP web server, whereas NGINX was designed to be both an HTTP web server and reverse proxy. You'll learn more about this later on in the course. Due to its design architecture, NGINX is able to handle concurrent connections much faster than Apache. Apache has a one connection per process model. This means server performance is significantly degraded when the number of concurrent connection requests surpasses the number of processes taking place. NGINX, on the other hand, was built specifically using an asynchronous and event-driven model capable of handling thousands of simultaneous connections. Because of its architecture, NGINX is unable to internally process dynamic content such as PHP. Instead, it passes it to an external processor for execution and waits for the rendered content to be returned. It then relays it back to the client. Apache, on the other hand, is built to process dynamic content within the server itself and independently of any external components. For the reasons above, Apache is best suited for dynamic content, whereas NGINX is best suited for serving static content. NGINX's connection handling mechanisms also make it perfect for use as a reverse proxy and load balancer. As for OS support, Apache is compatible with all major operating systems, including Linux, Mac OS, and Windows. NGINX is also compatible with most major operating systems, but may experience significant performance degradation when running on Windows. Apache supports distributed or decentralized configuration directives, whereas NGINX is centralized. This means that Apache is able to read configuration settings from a specific file within each directory, within the webroot folder. This file is referred to as a .htaccess file. NGINX does not have this type of built-in capability, and thus its configuration settings are always derived from a centralized configuration file. A decentralized configuration directive does offer some level of flexibility. However, it can also cause performance and security-related issues if not set up properly. However, if necessary, this pitfall can be entirely eliminated by turning off the .htaccess interpretation within the Apache configuration files. One of the biggest advantages to Apache over NGINX is its ability to dynamically load or unload modules based on the ever-evolving needs of each application. Also, since Apache remains one of the oldest web server technologies around, it offers an extensive library of modules that are well supported through its open source community. Modules offer the ability to add functions such as data encryption, URL rewriting, client authentication, logging, caching, compression, proxying, and much more. NGINX, on the other hand, lacks the ability to dynamically load modules. Instead, modules that are not included in the standard distribution package must be selected and compiled into the core software prior to installation. This means that it's very important to consider which modules may be required at some point in the future during the initial configuration of the server. Both NGINX and Apache offer vibrant communities with plenty of documentation for support. Although due to its age, Apache does triumph in this category. Many of the document libraries for NGINX were originally written in Russian, which presents an issue for developers seeking support in English. However, as the prevalence of NGINX continues to rise, this gap continues to narrow. Although we focused on exploring the key differences between Apache and NGINX, the two technologies are often used together as shown in this illustration. By doing so, we leverage the strengths of each server while overcoming their individual limitations. As seen in the diagram, one of the most common methods of integrating Apache and NGINX is by placing NGINX in front of Apache to handle all incoming HTTP requests. From there, NGINX can relay requests for dynamic content over to Apache while serving requests for static content by itself. This method of integration between Apache and NGINX is known as a reverse proxy configuration. Here, we're taking advantage of NGINX's ability to rapidly process large volumes of simultaneous connection requests. At the same time, we alleviate some of the strain on Apache by reducing the number of open threads and processes which can degrade Apache's performance. Later in this course, we will demonstrate how to deploy this type of configuration to efficiently host multiple websites on a single server. Welcome. In this lesson, we'll provide you with an introduction into databases. Whether you're taking this course as an aspiring full-stack developer or cloud administrator, it's very likely that you will work in some capacity with database software. By now, you're familiar with Apache. You know that it's an open-source HTTP server designed to serve web content. Most dynamic web applications that run on Apache interact with databases in order to deliver customized user experiences. For example, when you log into your favorite social media site, all the content visible to you is custom tailored based on your browsing habits and other site interactions. Just about any information you supply in your user profile and other actions you perform on social networking sites are stored in a database. This includes things like messages, likes, image posts, and more. As you can imagine, the volume of information stored in these databases is quite impressive. To put it into perspective, Statista reports that Facebook alone had close to 3 billion users worldwide as of last year. This includes 2.41 billion monthly active users as reported by HubSpot. This level of traffic translates into an enormous volume of data. Facebook generates 4 petabytes of data per day. That's the equivalent of 1 million gigabytes. Though it's difficult to quantify the exact numbers, it's safe to assume that a significant portion of this data is stored in a network of databases distributed around the world. Although it's quite unlikely that most developers will work with data sets as complex as Facebook, the concepts of data storage and retrieval are universally applicable to applications of all sizes. So what is a database? As defined by Oracle, a database is an organized collection of structured information or data typically stored electronically in a computer system. A database is usually controlled by a database management system or DBMS. Together, the data and the DBMS, along with the applications that are associated with them, are referred to as a database system, often shortened to just database. The DBMS allows applications and users to retrieve, update, and manage how information in the database is organized and optimized. The DBMS also offers the ability to perform additional administrative operations on databases such as monitoring, tuning, backups, and recovery. When it comes to databases and DBMSs, there are several varieties and not all were created equal. Furthermore, each DBMS solution has different pros and cons depending on the use case. Since this course will be more focused towards the use of databases in the development of web applications, we'll mostly be concerned with 2 categories of database types, including relational, also known as SQL, and non-relational, also known as NoSQL databases. Welcome back. In this lecture, we'll provide an overview of the key characteristics of SQL versus NoSQL databases. We'll also explore different DBMSs that are growing in popularity within the development community. This chart provides a clear snapshot on the key differences between SQL and NoSQL databases. We know that relational database transactions follow the ACID principle, whereby non-relational databases follow the CAP theorem. Although some NoSQL databases do claim support for ACID transactions, the interpretations of this are rather vague. SQL databases scale up, whereas NoSQL databases scale out, allowing for parallel processing across multiple nodes. SQL databases store data in tables with fixed rows and columns. NoSQL databases employ different structures, but the most common NoSQL data store is the document database, which uses JSON documents composed of key value pairs. The non-relational, or SQL database, was developed in 1970 with the purpose of reducing data duplication. NoSQL databases were developed much later in the 2000s for the purpose of scalability in rapidly processing large data sets with simple queries. SQL databases offer rigid data storage design schemas, whereas NoSQL databases are much more flexible. SQL databases require a great deal of optimization. SQL databases require a great deal of optimization, indexing, and other configuration to reach the performance of NoSQL databases. The last item listed here is an important one to note. SQL databases support very complex joins to combine rows from two or more tables for the purpose of executing complex queries. NoSQL databases generally only support simple queries and limited join operations. We'll be working with joins later in the app development portion of this course. Now that you're more familiar with the characteristics of SQL versus NoSQL databases, let's take a look at some popular database options within each category. Since there are constantly new DBMSs emerging, it's generally a good idea to consult a third-party resource that keeps track of what's new in the industry. One such resource can be found over at dbengines.com. So let's go ahead and I'll pull up that resource. This website offers a visual classification of different database types based on popularity through tables and graphs. We can also narrow our criteria for comparisons based on the categories on the left navigation menu. For example, we can see popularity comparisons amongst all DBMSs, or we can narrow the results based on relational versus non-relational DBMSs. All the values relevant to rankings are updated monthly. We can also see the method used for ranking by clicking the method link. You can go through this page if you want more information, but for now, I'll go ahead and go back because we don't need to cover it in detail for now. If we go ahead and click on the trend chart, it'll bring up the default graph that ranks all DBMSs regardless of their category. We can see that the top 5 are currently listed as Oracle, MySQL, Microsoft SQL Server, and PostgreSQL. Below PostgreSQL, we also have MongoDB, which is a very popular NoSQL database. The top 4, including Oracle, MySQL, MS SQL Server, and PostgreSQL, are all relational databases, whereas MongoDB is the only one in the top 5, which is a non-relational or NoSQL database. So that's an important point worth mentioning. Now let's go ahead and filter the results by comparing the popularity of only relational databases. So go ahead and click Relational DBMSs on the left navigation menu. Once the page loads, you'll see that the list remains unchanged except for the 5th item, which is changed to IBM DB2. Let's take a look at non-relational or document store databases. So just go ahead and find that on the left navigation menu, click Document Stores. In this category, MongoDB, Amazon DynamoDB, Databricks, Microsoft Azure Cosmos DB, and Couchbase rank as the top 5 NoSQL databases in terms of popularity. Now let's go ahead and click back over to the complete ranking section. While looking at these statistics, it's important to note that the current popularity ranking of a DBMS doesn't necessarily mean it's the latest technology or the best in terms of performance. In contrast, a high ranking could simply be due to the fact that it's the oldest technology and therefore has the highest rate of adoption over time. For example, MySQL was founded in 1995 and quickly became one of the most widely used open-source RDBMSs in the world. MySQL went from 1 million active users in 2001 to 100+ million copies downloaded or distributed in January 2010. It's worth noting that several enterprise-level applications like Facebook were originally developed using PHP along with MySQL as the primary data store. Other notable organizations that have employed MySQL in some form include Netflix, YouTube, Booking.com, and Airbnb. For this reason, it's no surprise that even to this day, MySQL is only second to Oracle in popularity. Although MySQL still remains available for use under a dual commercial license, the project's vendor, MySQL AB, was acquired by Sun Microsystems Incorporated in 2008. Sun Microsystems was subsequently acquired by Oracle in 2009. This acquisition caused concerns in the development community since Oracle Corporation remains one of the largest vendors of closed-source database technology. At the time, MySQL was also one of its biggest competitors. Fears started to circulate within the community from the possibility that MySQL would become proprietary or worse yet, discontinued altogether. For this reason, Michael Widenius, one of the original founders of MySQL, forked the project and founded MariaDB. The project was named after his daughter Maria, with the guarantee of remaining completely open source under a general public license. Furthermore, MariaDB was designed to be a full binary replacement or drop-in for MySQL. This would greatly simplify the process for developers of transitioning from working with MySQL to MariaDB. I'm back here on the statistics page, and an interesting observation is the growth rate of MariaDB in terms of popularity. If you click on the trend chart, here we can see an upward trend for MariaDB, whereas MySQL is flat or even declining. In addition to a trend in wider adoption, here are some of the major optimizations included in MariaDB over MySQL. These were detailed in an article published by hacker.io. MariaDB has higher overall performance with the ability to handle large amounts of data easily. It has higher performance in respect to database views, which are virtual database tables that can be queried like regular tables. Another advantage is linear scalability across instances in a database cluster, stemming from the column store distributed data architecture of MariaDB. The implementation of virtual columns, which is not available in MySQL, this gives MariaDB the ability to perform calculations at the database level, which improves speed when several applications are accessing a column at the same time. MariaDB also offers parallel query execution, also known as parallelism. This enables the execution of multiple database queries simultaneously. MariaDB offers thread pooling, which generates pools of open threads that database connections can quickly pick up when a query is performed. This is a significant enhancement from the one thread per connection architecture offered in MySQL. Thread pooling is currently available only in the commercial-grade MySQL Enterprise Edition. MariaDB offers powerful storage engines by default, including the XtraDB, Area, etc. With MySQL, these must be installed manually. So as you can see, MariaDB is a powerful drop-in replacement for MySQL, and it offers several performance optimizations. Furthermore, it remains true to the principles of an open source project, unlike MySQL. For this reason, we will focus on MariaDB as our relational DBMS of choice during the hands-on section of this course. Now, with that said, it might be very likely that the applications you intend to build require a non-relational or NoSQL DBMS solution. Two of the most common types of NoSQL databases you may work with include document stores and key value stores. So back over here on the statistics page, we can see that MongoDB is the most popular NoSQL document store database by far. Now let's go ahead and navigate over to the key value store database list. Go ahead and click over here. We can see here that Redis dominates this category. And for this reason, our demonstrations pertaining to NoSQL databases will focus on these two DBMSs. It's also important to note that in a key value store such as Redis, only the keys can be used to query the database. The values themselves are opaque, therefore the database store knows nothing about them. As we explored earlier, the document store database stores values in a readable structured format that the database can understand. Now let's do a quick comparison of various popular NoSQL database options and their characteristics. Looking at this table here, we can see that MongoDB is a document-based database that uses JavaScript as its primary query language. MongoDB is one of the very few NoSQL databases that boasts both single document and multi-document ACID-compliant transactions. Its use cases include web and mobile apps, the Internet of Things, product catalogs and inventory, and real-time analytics. MongoDB comes with 2 editions, one of which is open source. Now, Redis, on the other hand, is a key value store database. It's partially ACID compliant and is best used for data related to chats, messaging, machine learning, rich media streams, data filtering, and statistics. Redis is open sourced under a 3-clause BSD license and also offers a closed source enterprise edition. Couchbase and Amazon DynamoDB offer both document-based and key value stores. DynamoDB is proprietary to Amazon and thus not open source. Couchbase, on the other hand, is open source. Couchbase uses N1QL as its primary query language, whereas DynamoDB uses DQL. DynamoDB is partially ACID compliant, whereas Couchbase offers very limited ACID compliance. Both these database solutions are generally used for applications in financial services, rich media streaming, retail, IoT, and gaming. And lastly, we have Cassandra, which is a wide column store using CQL as its primary query language. It's not ACID compliant. Cassandra is, however, free and open source. Cassandra has been used in a range of applications from financial services to content management systems and messaging. Excellent job on making it this far. In this section of the course, you learned the following key concepts: the difference between relational, SQL, and non-relational, NoSQL databases, the ACID principle versus the CAP theorem, the structure of data in an SQL versus a NoSQL DBMS, statistics on various types of SQL and NoSQL databases, the difference between MySQL and MariaDB, and the characteristics of different types of NoSQL databases. In the next lesson, we'll explore some additional key terms that are instrumental towards your journey as a developer. Welcome back. In this lesson, we'll continue our discussion on SQL and NoSQL databases. Up to this point, you've gained a bit of familiarity between the differences in structure of data storage between the two database types. However, there's much more to it than just that. Let's take a detailed look at some of the major differences between relational and non-relational databases. The ACID principle for relational databases. Perhaps one of the most significant differences between SQL and NoSQL databases is the compliance standard that each database type employs to guarantee the reliability of database transactions. Generally speaking, relational databases use the ACID standard, whereas non-relational databases follow the CAP theorem. There are certain exceptions to this rule, as a few NoSQL DBMS solutions do offer ACID transactions on some level. We'll touch more on this later on. ACID is an acronym for atomicity, consistency, isolation, and durability. An article published by database.guide provides an insightful overview on each of these elements. Atomicity is described as the part of a database transaction that guarantees that either all of the transaction succeeds or none of it does. You can think of this as an all or nothing approach to data processing, whereby if one part of the transaction fails, the whole transaction fails. The second element in ACID is consistency. This is another important aspect of ACID. When a database processes transactions, it does so by following a set of rules and constraints to maintain data integrity. Should a violation of any of the rules occur, consistency ensures the process will be aborted and rolled back to its previous state. A very common type of constraint is the primary key declarative constraint. Here, the DBMS will ensure that each row has a unique value for a specific column and that the value is not null. There are more complex constraints and triggers that can be implemented as well. Banking applications often integrate some of the strictest constraints to ensure the integrity of customer account balances and other transactional information. The third element of ACID is isolation. Isolation means that all transactions that are processed within the DBMS are done so in isolation from one another. This way, no single transaction is affected by another. Data isolation ensures that transactions are prevented from reading data from any other transaction that is currently in queue for processing. The last element in the ACID standard is durability. To pass this metric, the DBMS must ensure that updates or changes made to successfully executed database transactions will survive permanently. This must be the case even in the event of system failures due to crashes or other similar issues. And that is the ACID principle in a nutshell. In the next lecture, we'll explore the CAP theorem, which forms a conceptual framework for the design of distributed data systems, which are the backbone of NoSQL databases. In this lecture, we'll explore the CAP theorem for NoSQL databases. One of the most significant advantages of working with NoSQL databases is their ability to scale horizontally across instances. This means that a NoSQL database can handle an ever-increasing traffic load by attaching it to more nodes, each equipped with CPU, RAM, and storage. This is one of the main reasons why NoSQL databases have gained momentum in the development community for applications that involve large, constantly evolving data sets. For example, artificial intelligence, the Internet of Things, and complex data analytics. Compare this to relational databases that are limited to vertical scalability. Here, computational resources can only be upgraded on the single instance hosting the database. Since NoSQL databases can be spread across distributed systems and harness the power of parallel processing, they fall under the transaction compliance of the CAP theorem. Unlike ACID compliance, the CAP theorem is based on the premise that a distributed data system can only achieve 2 out of 3 guarantees in the event of network failure. The 3 guarantees include consistency, availability, and partition tolerance, as illustrated in the diagram below. The points in which any 2 items intersect are identified as CA, CP, and AP. In CAP theorem, consistency means that every read request on a database receives the most recent write regardless of the instance the user is connected to in the distributed system. In order for this to happen, data written to one instance must be instantly forwarded or replicated to all other instances in the system before the write request is considered successful. The availability in CAP theorem means that all non-failing instances in the distributed system must be available for queries without exception. In other words, a non-failing instance should return a response for read and write requests within a reasonable time, even if other instances are down. The last component of CAP theorem is partition tolerance. This means that a distributed system must continue to operate even with system failure or data loss. This last element, partition tolerance, is predicated on the theory that a single instance failure should not result in the collapse of the entire system. In this lecture, you learn the difference between the ACID compliance principle and CAP theorem as applicable to SQL versus NoSQL databases. In the next lecture, we'll provide an overview of the key characteristics of both types of databases. Welcome back. In this lecture, we'll provide an overview of the key characteristics of SQL versus NoSQL databases. We'll also explore different DBMSs that are growing in popularity within the development community. This chart provides a clear snapshot on the key differences between SQL and NoSQL databases. We know that relational database transactions follow the ACID principle, whereby non-relational databases follow the CAP theorem. Although some NoSQL databases do claim support for ACID transactions, the interpretations of this are rather vague. SQL databases scale up, whereas NoSQL databases scale out, allowing for parallel processing across multiple nodes. SQL databases store data in tables with fixed rows and columns. NoSQL databases employ different structures, but the most common NoSQL data store is the document database, which uses JSON documents composed of key value pairs. The non-relational, or SQL database, was developed in 1970 with the purpose of reducing data duplication. NoSQL databases were developed much later in the 2000s for the purpose of scalability and rapidly processing large data sets with simple queries. SQL databases offer rigid data storage design schemas, whereas NoSQL databases are much more flexible. SQL databases require a great deal of optimization. Indexing, and other configuration to reach the performance of NoSQL databases. The last item listed here is an important one to note. SQL databases support very complex joins to combine rows from 2 or more tables for the purpose of executing complex queries. NoSQL databases generally only support simple queries and limited join operations. We'll be working with joins later in the app development portion of this course. Now that you're more familiar with the characteristics of SQL versus NoSQL databases, let's take a look at some popular database options within each category. Since there are constantly new DBMSs emerging, it's generally a good idea to consult a third-party resource that keeps track of what's new in the industry. One such resource can be found over at dbengines.com. So let's go ahead and I'll pull up that resource. This website offers a visual classification of different database types based on popularity through tables and graphs. We can also narrow our criteria for comparisons based on the categories on the left navigation menu. For example, we can see popularity comparisons amongst all DBMSs, or we can narrow the results based on relational versus non-relational DBMSs. All the values relevant to rankings are updated monthly. We can also see the method used for ranking by clicking the method link. You can go through this page if you want more information, but for now, I'll go ahead and go back because we don't need to cover it in detail for now. If we go ahead and click on the trend chart, it'll bring up the default graph that ranks all DBMSs regardless of their category. We can see that the top 5 are currently listed as Oracle, MySQL, Microsoft SQL Server, and PostgreSQL. Below PostgreSQL, we also have MongoDB, which is a very popular NoSQL database. The top 4, including Oracle, MySQL, MS SQL Server, and PostgreSQL, are all relational databases, whereas MongoDB is the only one in the top 5, which is a non-relational or NoSQL database. So that's an important point worth mentioning. Now let's go ahead and filter the results by comparing the popularity of only relational databases. So go ahead and click Relational DBMSs on the left navigation menu. Once the page loads, you'll see that the list remains unchanged except for the 5th item, which is changed to IBM DB2. Let's take a look at non-relational or document store databases. So just go ahead and find that on the left navigation menu, click Document Stores. In this category, MongoDB, Amazon DynamoDB, Databricks, Microsoft Azure Cosmos DB, and Couchbase rank as the top 5 NoSQL databases in terms of popularity. Now let's go ahead and click back over to the complete ranking section. While looking at these statistics, it's important to note that the current popularity ranking of a DBMS doesn't necessarily mean it's the latest technology or the best in terms of performance. In contrast, a high ranking could simply be due to the fact that it's the oldest technology and therefore has the highest rate of adoption over time. For example, MySQL was founded in 1995 and quickly became one of the most widely used open-source RDBMSs in the world. MySQL went from 1 million active users in 2001 to 100+ million copies downloaded or distributed in January 2010. It's worth noting that several enterprise-level applications like Facebook were originally developed using PHP along with MySQL as the primary data store. Other notable organizations that have employed MySQL in some form include Netflix, YouTube, Booking.com, and Airbnb. For this reason, it's no surprise that even to this day, MySQL is only second to Oracle in popularity. Although MySQL still remains available for use under a dual commercial license, the project's vendor, MySQL AB, was acquired by Sun Microsystems Incorporated in 2008. Sun Microsystems was subsequently acquired by Oracle in 2009. This acquisition caused concerns in the development community since Oracle Corporation remains one of the largest vendors of closed-source database technology. At the time, MySQL was also one of its biggest competitors. Fears started to circulate within the community from the possibility that MySQL would become proprietary or worse yet, discontinued altogether. For this reason, Michael Wydnius, one of the original founders of MySQL, forked the project and founded MariaDB. The project was named after his daughter Maria, with the guarantee of remaining completely open source under a general public license. Furthermore, MariaDB was designed to be a full binary replacement or drop-in for MySQL. This would greatly simplify the process for developers of transitioning from working with MySQL to MariaDB. I'm back here on the statistics page, and an interesting observation is the growth rate of MariaDB in terms of popularity. If you click on the trend chart, here we can see an upward trend for MariaDB, whereas MySQL is flat or even declining. In addition to a trend in wider adoption, here are some of the major optimizations included in MariaDB over MySQL. These were detailed in an article published by hacker.io. MariaDB has higher overall performance with the ability to handle large amounts of data easily. It has higher performance in respect to database views, which are virtual database tables that can be queried like regular tables. Another advantage is linear scalability across instances in a database cluster, stemming from the column store distributed data architecture of MariaDB. The implementation of virtual columns, which is not available in MySQL, this gives MariaDB the ability to perform calculations at the database level, which improves speed when several applications are accessing a column at the same time. MariaDB also offers parallel query execution, also known as parallelism. This enables the execution of multiple database queries simultaneously. MariaDB offers thread pooling, which generates pools of open threads that database connections can quickly pick up when a query is performed. This is a significant enhancement from the one thread per connection architecture offered in MySQL. Thread pooling is currently available only in the commercial-grade MySQL Enterprise Edition. MariaDB offers powerful storage engines by default, including the XtraDB, Area, etc. With MySQL, these must be installed manually. So as you can see, MariaDB is a powerful drop-in replacement for MySQL, and it offers several performance optimizations. Furthermore, it remains true to the principles of an open source project, unlike MySQL. For this reason, we will focus on MariaDB as our relational DBMS of choice during the hands-on section of this course. Now, with that said, it might be very likely that the applications you intend to build require a non-relational or NoSQL DBMS solution. Two of the most common types of NoSQL databases you may work with include document stores and key value stores. So back over here on the statistics page, we can see that MongoDB is the most popular NoSQL document store database by far. Now let's go ahead and navigate over to the key value store database list. Go ahead and click over here. We can see here that Redis dominates this category. And for this reason, our demonstrations pertaining to NoSQL databases will focus on these two DBMSs. It's also important to note that in a key value store such as Redis, only the keys can be used to query the database. The values themselves are opaque, therefore the database store knows nothing about them. As we explored earlier, the document store database stores values in a readable structured format that the database can understand. Now let's do a quick comparison of various popular NoSQL database options and their characteristics. Looking at this table here, we can see that MongoDB is a document-based database that uses JavaScript as its primary query language. MongoDB is one of the very few NoSQL databases that boasts both single document and multi-document ACID-compliant transactions. Its use cases include web and mobile apps, the Internet of Things, product catalogs and inventory, and real-time analytics. MongoDB comes with 2 editions, one of which is open source. Now, Redis, on the other hand, is a key value store database. It's partially ACID compliant and is best used for data related to chats, messaging, machine learning, rich media streams, data filtering, and statistics. Redis is open sourced under a 3-clause BSD license and also offers a closed source enterprise edition. Couchbase and Amazon DynamoDB offer both document-based and key value stores. DynamoDB is proprietary to Amazon and thus not open source. Couchbase, on the other hand, is open source. Couchbase uses N1QL as its primary query language, whereas DynamoDB uses DQL. DynamoDB is partially ACID compliant, whereas Couchbase offers very limited ACID compliance. Both these database solutions are generally used for applications in financial services, rich media streaming, retail, IoT, and gaming. And lastly, we have Cassandra, which is a wide column store using CQL as its primary query language. It's not ACID compliant. Cassandra is, however, free and open source. Cassandra has been used in a range of applications from financial services to content management systems and messaging. Excellent job on making it this far. In this section of the course, you learned the following key concepts: the difference between relational SQL and non-relational NoSQL databases, the ACID principle versus the CAP theorem, the structure of data in an SQL versus a NoSQL DBMS, statistics on various types of SQL and NoSQL databases, the difference between MySQL and MariaDB, and the characteristics of different types of NoSQL databases. In the next lesson, we'll explore some additional key terms that are instrumental towards your journey as a developer. Welcome back. In this lesson, we'll take a look at a few key terms that are important to understand before diving into the hands-on exercises. Before we go over them, let's do a quick recap of some of the major concepts we've explored so far. Here's what you should know up to this point. First, the Linux kernel comes in a variety of distributions, also known as distros. Apache and NGINX are 2 popular web server software packages that are commonly used with Linux-based systems. Modern DBMSs fall into 2 categories, including relational, or SQL, and non-relational, or NoSQL. Hopefully that all sounds familiar to you. Hopefully that all sounds familiar to you. With that in mind, let's go over the new terms that we will be referring to moving forward. The first term is software stack. As we move on to server configuration, we'll be working with a number of software stacks. As defined by TechTarget, a software stack is a collection of independent components that work together to support the execution of an application. A software stack can include a number of different components, but generally encompass the operating system, databases, scripting languages, runtime environments, and architectural layers. These components communicate directly with applications hosted on the server through complex instructions that travel through the stack. One of the most common software stacks used in web development is LAMP stack. This software stack generally encompasses the following components: Linux, Apache, MySQL, and PHP. It's important to note that these components are largely interchangeable. For example, MySQL is sometimes replaced with MariaDB, whereas PHP is commonly interchanged with Perl or Python. At times, Apache is also substituted with NGINX, which then becomes LEMP stack. Since LEMP stack and LAMP stack are two of the most popular software stacks, you'll come across these acronyms frequently when working with various cloud providers. For example, Linode offers the ability to automatically install LAMP and LEMP stack on server deployment through the Linode marketplace. Two other software stacks which have gained tremendous popularity in recent years include MERNStack and MEANStack. MERNStack is an acronym for MongoDB, Express.js, React.js, and Node.js. MEANStack is identical to MERN with one exception: React.js is swapped with AngularJS. Both Mean and MERNStack have gained widespread adoption in the development of web apps because each component within the stack from front to back end is based on JavaScript. Let's go over the different components of each of these software stacks, excluding MongoDB since you're already familiar with it. We covered it a bit in the database section of this course. We'll start with React.js. React is an open source JavaScript library which is typically used to build front-end user interfaces on single-page applications. React is free, open source, and maintained by Meta, along with a community of individual developers and companies. React.js is quickly becoming one of the most popular JavaScript libraries for building user interfaces. Next, we have AngularJS. Angular is an entire open source JavaScript framework managed by Google. We'll explore the difference between libraries and frameworks later in this module. Both React.js and AngularJS can be used for mobile and web apps. However, the learning curve for Angular is much steeper. React is generally used to build UI components, whereas AngularJS is a structural framework for developing dynamic web apps. Another key difference is that Angular is based on TypeScript, whereas React is based on JavaScript. TypeScript is a strict superset of JavaScript, which requires additional learning even for developers with a background in JavaScript. Next, we have Node.js. Node is a JavaScript runtime environment which is used to run JavaScript code on the server side outside the web browser. This advancement has been seen as revolutionary within the development community since JavaScript has traditionally been locked out of the server-side operations. Node.js is cross-platform meaning it runs on just about any operating system. Node.js was authored by Ryan Dahl and remains free and open source under an MIT license. Lastly, we have Express.js. This is a web application framework that operates on top of Node.js. Express.js makes the development of Node.js backend processes faster and easier. Express.js is freely available for use under an open source MIT license. Welcome back. To continue on our last discussion, the next important terms we'll talk about are framework and library. Throughout much of this course, we'll be using the terms framework and library when exploring different scripting and programming languages. In some cases, you may even see the terms loosely used interchangeably within development communities. With that said, it's important to know the technical difference between these two terms and what each one is used for. Otherwise, things can start to become a bit confusing. Firstly, both frameworks and libraries do share one important commonality. They are both code written by you or a third party that helps solve common problems. A library can be as simple as a single reusable function that automatically removes spaces from a block of text when executed. Now that's just an example. A library is designed to eliminate repetitive tasks by creating reusable code. When using a library, you're still very much in control of how the application is modeled, meaning you retain full control over the flow of code but make calls to the library when needed. A few popular JavaScript libraries include React.js, Material UI, and jQuery. Now, a framework, on the other hand, is a bit different. When developing an application using a framework, the framework will control the flow of the code. This is also referred to as an inversion of control. Frameworks offer a rigid system to ensure certain protocols are met during the development process. Here, the developer only needs to plug in code where necessary as defined by the architecture of the framework. The flexibility of a framework is often referred to as opinionated or unopinionated. A more opinionated framework would be less flexible in regards to the discretion a developer has over the flow of code. The subjectiveness of this area sometimes makes the process of distinguishing between a framework and library a bit more challenging. For example, a framework which offers a high degree of control to the developer can be difficult to distinguish from a library. With that in mind, here are a few popular frameworks modeled around various scripting languages. Popular JavaScript frameworks include AngularJS, Vue.js, and Express.js. Now, as for PHP frameworks, popular ones include Laravel, CodeIgniter, CakePHP, and Symfony. Popular Python frameworks include Django and Flask. Now that you're familiar with the difference between frameworks and libraries, let's move on to programming versus scripting languages. And we'll see you in just a minute. Another source of confusion for aspiring developers when it comes to coding is the difference between client-side and server-side scripting languages. It's important to distinguish between the two, since each language you work with will generally fall within one of these two categories. Knowing the difference will help you determine the language most suitable for your project or application. To begin, a scripting language is sometimes referred to as an interpreted language because they are interpreted at runtime rather than compiled beforehand. Most modern scripting languages are open source and cross-platform compatible. This means they can run on just about any major operating system or web browser without the need for any type of special software. There are two main types of scripting languages, including server-side and client-side. A server-side scripting language is interpreted by a web server to perform logical and algorithmic back-end operations. Examples of scripting languages within this category include PHP, Python, Node.js, Ruby, and Perl. All these languages can be used to develop dynamic web pages that communicate directly with the web server, in order to relay instructions on how the code should be executed. A common use case for server-side scripting languages is to facilitate communication between the web application and database. Other common use cases include login/logout operations, session management, and processing user queries. Client-side languages, on the other hand, do not communicate directly with the web server. Instead, they do exactly as the name suggests. They execute code at the client level, for example, in your web browser. Client-side languages are sometimes also referred to as front-end languages because they control what the user sees through their web browser. The text elements, images, video, and other UI components that make up a web page are all governed by client-side languages. Two client-side languages that are used for this purpose are HTML and CSS. Although they are often referred to as client-side scripting languages, a more applicable term for HTML and CSS are client-side markup languages. This is because both HTML and CSS only define the structure of data on a web page, which doesn't require the interpretation of any logic or algorithm. JavaScript, on the other hand, is a truly client-side scripting language because it's able to relay client-side processes in an algorithmic fashion to dictate web page behavior. For a good example of how HTML, CSS, and JavaScript are interpreted by a web browser, let's head over to Airbnb.com. On the Airbnb homepage, HTML and CSS govern the location of text, colors, and other static visual elements on this page. If we hover our mouse over the images and links, we can see a few interactive events. For example, hovering our mouse over the buttons in the navigation menu causes the background color to change. It goes from light gray to a darker black color. Now, clicking on the profile icon, we can see that a drop-down menu appears. These types of interactive elements are an example of JavaScript at work. Excellent. In this lesson, we went over a number of key terms that will be helpful as you progress through the remaining modules in this course. In the next lecture, you'll gain some hands-on experience with installing a software stack on the Ubuntu Linux distribution.